Is this clear? Please check it. So field because of point sources, or ultimately we'll say spherical sources, is spherically symmetric. Field because of line charge as the source or cylindrical charge as the source. Later on the continuation, I will definitely extend it, is spherically symmetric. Line charge or cylindrical charge. The field because of line charge or cylindrical charge is cylindrically symmetric. To derive the expression for a given quantity, for a field with cylindrical symmetry, we need to use cylindrical coordinate system. And for a field with spherical symmetry, we need to use spherical coordinate system only. That's why everything in antennas and wave propagation, where it's basically a huge hemisphere, with antenna being a small line, can be considered as a point, because of which the natural coordinate system that we use is always spherical coordinate system. Everything is defined in spherical coordinate system only for antennas. Is this clear? I will extend this symmetric discussion because we have to do mathematical derivations to support things. We have to derive so many things. And it becomes extremely important for us to understand this symmetry. Listen carefully. Next level of symmetry to which we will move. Consider an equilateral triangle. Equilateral triangle. I'll just talk about it like this. It appears like this from somewhere. It's a triangular pyramid. And the vertex of this pyramid is above the centroid of this equilateral triangle. Now I can basically talk about this vertex at any height. But the base of this is a triangle, prism. With equal charges, here another level of symmetry to which we should go, kept at the vertices of this equilateral triangle. This vertex, which is above its centroid, will be at the same distance d from each charge. If I keep a small charge q, that small charge q in this particular case will experience only vertical component of the force. Why so is the point. Each side, when it comes from that particular charge, will make certain angle, same angle theta from vertical. You agree with this, no? And the force F at the magnitude of capital Q, small q divided by 4 pi epsilon d squared. D is the distance from each charge. If theta is the angle made by that radius vector from the vertical line, F vertical is 3 times sine theta. You agree this? Because all the forces are inclined at the same angle theta from the vertical. Oh, 3 cos theta, sorry. From the vertical only we give, because of its 3 cos theta. Cos theta is the component into the. What is the horizontal component of the resultant of these forces? F horizontal is equal to 0. Why 0? The horizontal components of these forces, if I basically take, they are separated by an angle of 120 degrees each. And the magnitude is F sine theta. If 2 forces are acting on an object, 2 equal forces, with an angle between them is equal to 180 degrees, which is 360 by 2. Resultant is 0. If 3 forces, no, they basically form a closed triangle with 120 degrees, right? Which is equal to 360 by 3. Resultant is 0. And we are sure that if there are 4 forces, equal forces in 4 directions, no, separated by an angle of 90 degrees from each. What is the resultant of these 2 forces? 90, which is equal to 360 by 4. Resultant is 0. If there are 5 with angle between the successive vectors equal to 360 by 5, resultant is equal to 0. You know that, right? In this particular case, you have 3 forces, right, from 3 different corners going and becoming horizontal. When they become horizontal, they are separated by an angle of 120 degrees from each other. Please check whether you are comfortable with this statement or not, because of which any charge Q kept at the vertex of this pyramid triangular pyramid it is, experiences 0 force in the horizontal direction. In the vertical direction, each component, each force will contribute capital Q, small q, cos theta by 4 pi epsilon d squared. It is not 3 times the horizontal component of each force because they are separated by 120 degrees each. In the same way, if I talk about a square pyramid, with its vertex again above the centroid of this, definitely with the charge Q kept at each of the corners, each charge is at the same distance, and the radius vector joining the charge small q and capital Q is inclined at the same angle from the vertical, because of which, if that angle is theta, from the vertical I'm measuring, and the distance is capital D, definitely depends upon the height of it, right? For a given square, each charge exerts the force equal to capital Q small q divided by 4 pi epsilon d squared. The vertical component Fb is equal to 4 times capital Q small q cos theta, and horizontal component is 0 because I will get this case. In fact, now I will talk about one more thing. If two charges are there kept along a straight line, at any point on the line, perpendicular line bisecting the line joining these two charges, if this is R, this is R, at every point, if I say this is Q, and this is small q, these two are two forces which aid each other's vertical component, but horizontal components are there in equal and opposite directions, because of which at any point on the perpendicular bisector of the line joining these two charges, any charge experiences only the vertical force, horizontal force becomes equal to 0. That way, if you see a diagonally opposite charges and the vertex is exactly above the center of the line joining diagonally opposite charges, I can divide these four charges into two sets of two charges, the lines joining which are mutually perpendicular because it is a square. Definitely they are at the same distance, because of which there will be no horizontal component. There will be only vertical component. Please check. In the same way, now carefully, the extended cases of it. If I have a circle of radius r, circular pyramid now, cone it is now. Base is a circle. If I keep n charges separated by equal distance along this circle, at any point on this axis passing through its center, there are n charges. If this is h in this particular case, if this is r, each charge is at the same distance root of r square plus h squared, and the angle made by the radius vector joining any charge with the point is same theta. The total force experienced by the charge small q because of all capital Q's is what? N times capital Q small q divided by 4 pi epsilon r square plus h squared cos theta, axial force or vertical force in this case. Now you can see that the horizontal components are, there are n forces with an angle between successive force being equal to 2 pi by n. N equal amount of horizontal components, no sin theta components. And they are separated, n forces separated by an angle of 2 pi by n, resulting 0 horizontal component of the force. Check it. So at any point on its axis, the field is axial. If it is a circular source. Is this clear? spoke about, listen carefully, Coulomb's law. First of all, as a force experienced by one point charge because of the other. Then we moved on to the superposition principle, where we spoke about the force experienced by one charge as the resultant of the individual forces experienced by that charge because of each charge. Resultant of the individual forces. Resultant is what? Resultant, or we know resultant of vector quantities is vector sum of. Plus we will keep A plus A bar plus B bar. It is vector sum. You should understand A bar plus B bar as its resultant of n forces, or n minus 1 forces, many forces, of number of forces. Okay. I gave this statement. Then I spoke about few cases. Then we moved on to something called as symmetry of the force field, taking different cases. And then the direction of the resultant in the regular systems of charges. Now listen. When I say the resultant of a number of forces, please concentrate. If there are two forces, we can calculate the resultant of these two forces using parallelogram law of vectors. If there are more number of forces, the resultant of which is to be determined, we need to use the component method, where each force is represented in the resolved form and the respective components are added to get the net force. We know that. Till now, we spoke about that version of the Coulomb's law, which only give you the magnitude of the force. As a formula, we will use capital Q small q divided by 4 pi epsilon d squared to calculate the magnitude. By seeing the figure, I will calculate the distance. I will calculate the angle. I will calculate the components and then add them. Once again, in the case discussed till now, there were the applications of scalar form of Coulomb's law, where I have the formula to compute only the magnitude of the force. Looking at the system of charges, I should check whether it is repulsive or attractive, then resolve them into components, calculate the resultant. Even the procedure of resolving them into individual components become really tedious if there are many charges creating a field. Irrespective of the number of charges, if you want to have a simple procedure to calculate the resultant of the number of forces, in the first take only, we have to represent, we have to get by using the so-called vector form of Coulomb's law, the vector force in the resolved form itself. If I can straight away get the force experienced by a given charge small q because of ith charge capital Q in the resolved form straight away, resultant is just addition of their respective components. The version of Coulomb's law that gives you the force in the resolved form is vector form of Coulomb's law. Of course, here we need to give the positions where the charges are kept in the given coordinate system also. Vector form, it straight away gives, without any ambiguity, the magnitude, direction of the force. It gives their components also. That means it calculates the force and resolves them into standard components and then give it to you. And true irrespective of whether the charges are positive, charges are negative, whatever it is. Now consider, because even though there is a system of charges, to calculate the force on a particular charge, we need to calculate the force because of each. Consider the case where charge Q1 is kept at a point P1, the coordinates of which is known to you. Another point P2, where the charge Q2 is kept. Listen carefully. While developing this particular law, we will assume that these two charges are both positive charges. Standard expression, please check now. Standard expressions are derived for positive sources. Ultimately, if some negative source is given, that particular variable is substituted with its sign. It works. That's where vector form is excellent and wonderful. I will develop the force and charge Q2 as a vector force in the resolved form. Please check it. Knowing the fact that any vector V bar is equal to what? Modulus of V bar into unit vector along V, correct? Any vector V bar is its unit vector that gives the direction of it, of unit magnitude, multiplied by the magnitude of that particular vector. Listen carefully. To determine the force on Q2, I will talk about the vector R12 bar. Going from 1 to 2, position vector of point P2 with respect to P1 is R12 bar. Listen carefully. I want to talk about the force on Q2. Because Q1 and Q2 are assumed to be positive, the force is in this direction specified by R12 cap, which is R12 bar divided by modulus of R12 vector. Correctly, no? I got the unit vector in the direction of the repulsive force experienced by the charge Q2. The repulsive force acts along R12 cap, and the modulus of the force F is equal to what? Q1 Q2 divided by 4 pi epsilon. Distance between them is mod R12 bar whole squared. Because I know the vector from P1 to P2. The distance between the points P1 and P2 definitely is the magnitude of the vector from P1 to P2 called as R12 bar. F bar is Q1 Q2 by 4 pi epsilon R12 bar whole squared. F modulus of F. What is F bar is equal to modulus of F into R12 cap, which is equal to Q1 Q2 by 4 pi epsilon mod R12 cubed by R12 cap is into R12 bar. R12 cap I should have kept. This is actually what? Q1 Q2 R12 cap divided by 4 pi epsilon mod R12 bar squared. R12 cap because it is R12 bar divided by mod R12. Now this R12 bar or R12 cap is in the resolved form. The remaining expression is a scalar sum only. Check it once. Vector form of Coulomb's law. Now please see this. This is actually good for you. We assumed Q1 and Q2 to be positive charges and developed the expression for the vector force experienced by Q2. Force on Q2, I will keep it as F1 bar, F bar. What is the force on Q1? Force on Q1 is minus F bar because they are equivalent opposite. Now please concentrate. This formula works irrespective of the polarities of the charges. If Q1 and Q2 are indeed positive charges, definitely the force experienced by Q2 is repulsive force. If both are negative also, force is repulsive. If one is positive and another is negative, force becomes attractive, which is minus of the repulsive force. If you look at this product Q1, Q2 in the expression, if you substitute these charges with their signs, your force with proper direction will come. R12 bar is taken. If Q1 and Q2 are both positive or negative, the product is positive because of which it is repulsive force along R12 bar. If one is positive, another is negative, product is, if you substitute them with their signs, the product is negative. Magnitude will remain the same. Minus of R12 bar is what? Exactly in the opposite direction to it. With, carefully, R12 bar having its components in meter, in meters. charges Q1 and Q2 in coulombs substituted with their signs, we get the correct force vector for any combination of charges. Is this clear? Both positive, both negative, one positive, one negative. It will give. We need not really worry about whether it is repulsive, attractive, and all. They are all taken into the form. Any vector formula, whenever you basically use, you have to substitute the sources with their signs. Very important point for us from now on. We always get it for a positive source. Assume for a positive source, develop the formula. When you substitute with the polarity or the sign. This is the vector form of Coulomb's law. So while calculating the net force using superposition, I will try to know the coordinates of the points where the charges are kept, and the coordinate the point where the test charge is kept, small q. I will use this vector law to calculate the individual force straight away in the vector form without really worrying about the components, attractive and repulsive forces. Add them by components, because we know that so many vectors represented in the standard resolved form will have the resultant obtained by adding the respective components. This is one point. Check it. Any doubts here? Please ask. Vector form is advantageous for us, because we need not take the components and add them to determine the resultant. Straight away, we will get it in the component form, because of which only thing that we have to do is addition to determine the resultant.